Hi, my name is Marco Comunità and I'm here to talk about the design of NeuraFuzz. NeuraFuzz is an analog neural fuzz distortion effect. It's analog because it's an original fuzz distortion circuit I designed drawing on my experience with and passion for audio analog electronics. And it's neural because I use the data from the circuit to train a neural network. But let's go step by step. I first started by designing an analog circuit, which you can see in the background, that captures the timbre of vintage germanium transistors fuzz pedals, while also removing the typical limitations of those old designs. In fact, typical fuzz pedals are known to sound good only at high gain settings, limiting the flexibility and the range of sounds achievable. Also, those designs are not very responsive to the player's dynamics. But let's wait for the demo and you'll be able to judge by yourself whether I achieved my goals. The principle behind the characteristic dynamic behavior of this design is similar to those applied for dynamic range compression. The circuit is based on a sidechain that detects the input signal envelope and generates a DC offset at the input of the clipping circuit. To control the overall timbre and feel of the distortion, the loudness sidechain needed to be adjusted to the amplitude and frequency of the signal. Also, the attack and release times with which we apply the DC offset have a massive impact on the timbre and the sustain. In addition, this sidechain-based design allows to decouple the amount of distortion from the amount of quote-unquote fuzz sound. Once I was happy with the circuit design, I generated the training data by running the SPICE circuit simulation using guitar signal as the input to the simulation itself. I sampled a total of 85 combinations of gain and attack and release time. I intentionally sampled the data very densely for low gain settings because I wanted to have a very smooth increase of distortion. And I ended up generating about 5.5 gigabytes of training data. The neural network I adopted to model the fuzz was proposed in a recent paper I published as part of my current PhD research, and it's a modification of a known autoregressive implementation of a WaveNet convolutional network. This model has been shown to work well to emulate distortion circuits that require a short receptive field. But to capture the long time range dynamic behavior induced by the sidechain of my design, I used so-called temporal feature-wise modulation layers. Temporal film is implemented using single LSTM layers whose output is used to modulate the activations of each convolution layer. The final result is a black box distortion modeling network that is able to capture the complex time-dependent behavior of my circuit design. As we can see in this block diagram, the so-called gated convolution network is made of several blocks. Each block includes a series of dilated 1D convolutions, and the outputs of each convolution are sent to a mixing layer to generate the final output. As we can see here, the picture on the left shows the detailed implementation of each convolution layer, which, together with the dilated 1D convolution, includes a gated activation. This is where we modify the model and insert the temporal film layer, which receives the output features from the gated activation and generates the modulation factors that are multiplied with the activations themselves. Internally, each temporal film layer includes a max pool 1D layer that downsamples the input by 128 times, allowing to capture long time range dependencies without introducing artifacts in the process sound. As we can see, each input block of 128 samples is multiplied by one of the outputs of the LSTM layer. Also, to make our model controllable, we inject the conditioning parameters, in our case gain and fuzz controls, at the input of every LSTM layer, so that they affect the modulated output. The final architecture was trained for a couple of days, and to export the model, I opted to use the Newton SDK, which required the 1D convolution layers to be replaced with cached convolutions so that the network could work with a continuous stream of frames while retaining the past context. Also, to add extra mojo to my NeuraFuzz, for that Jack White Black Keys sound, I also decided to add a ring modulator using good old digital signal processing. While the neural network takes care of the distortion, I added the necessary code to implement a simple ring modulator, which is only applied to the clean signal. In fact, applying it to the distorted output wasn't giving me the right tone. To conclude, the NeuraFuzz has four main controls: gain, which determines the amount of distortion; fuzz, which sets how fuzzy and gated the distortion sounds; fuzz ring modulation blend, which sets the mix between distorted fuzz and the ring modulated clean; and ring frequency, which sets the ring modulator oscillator frequency. Thank you for listening to all these details, and now off to the demo with my friend and great guitarist Andrea.